Officially recording now. And okay, can everyone see the title slide, differential mode conducted emissions?
Yes.
Yes.
Okay. All right, so I have this in two separate presentations for differential mode and common mode. But if time permits, I'm going to cover the theoretical portions of both of these today. And then next week in the lab, we'll cover the lab portion of both today. At least that's the intent. So we'll see how much of this we can get through. So today's presentation is all about conducted emissions, encompassing both differential mode and common. Okay, so getting on with it. We will start with Kirchhoff's current law. This is and if I can ask everyone to mute your mics, please, unless you're asking a question, minimizes background noise. So with Kirchhoff's current law, that it tells us that all currents return to their sources, or the maybe the official way of saying it is that the sum of all currents in or out of a given node must equal 0. And I've sometimes said this is true because Kirchhoff says so. Kirchhoff's just the messenger. Mother Nature says so. I mean, this is a law of nature and a law of physics, and it's immutable. You have no choice in the matter. So all currents will return to their sources is just a different way of expressing this, that any current going out of a node must have the same current coming back into it. So current will follow all available paths in inverse proportion to the relative impedances of the different paths. That's a bit of a mouthful. People like to say current follows the path of least resistance, but that is not a true statement. Or it's only true, well, it's really not a true statement at all. It's not always the path of least resistance. And even in a DC sense, where the current will still follow every available path. If you have a 1 volt source and a 1 ohm load, okay, you're going to get 1 amp through that load coming back to the source. Well, you put 1 kilo ohm in parallel with the 1 ohm. That doesn't mean that all current's going to flow through the 1 ohm resistor. You're still going to get a milliamp flowing through that 1 kilo ohm path back to the source. It's 1,000th of what you're getting through the 1 ohm load, but it's still some measurable, tangible amount of current. And that 1 milliamp could be causing some disruptions to whatever that path is, right? So this current flowing the path of least resistance is really something that we need to purge from our lexicon. It's not a true statement. It follows all available paths in inverse proportion to relative impedances, and that impedance is frequency dependent. So we look at a simple circuit model. We have some voltage source and a load, and you'll have a send and a return path. So the differential mode current is traditionally what we think of as the current that returns to the source on the intended path, which is generally a dedicated wire, dedicated conductive path. And then common mode current is the current that will return to the source on an unintended path. So it could be some leakage capacitance to structure. Structure is a common, as it were, a common path for common mode current. It's not the only path, but it's certainly a very common path where you have any leakage capacitance. Because you remember, we're talking about frequency dependence here. So at higher frequencies, those currents will find capacitively coupled paths to nearby conductors. And so that common mode current is basically what we define as any of that current that's follows some other path back to the source than the intended one. And this there could be a virtual capacitor here too. So it's the thing with common mode currents, especially higher frequency common mode currents, they will find capacitive coupled paths. You're not necessarily talking about a conductor. Okay. The first part of this discussion is going to focus on differential mode current. So a traditional conducted emissions measurement is shown here, where we put a current probe around each individual wire. So it's showing around the send wire first, and then you would make a measurement around the return wire separately. Thing is, when you do this, you're measuring all of the current on that wire. It's measuring both differential mode and common mode current. You have no idea which is which. You're just measuring all of the current on that wire as one composite measurement. And you make the measurement separately on the positive and return leads. So that's two measurements that you're making per the traditional way of doing it. So from the Marshall Space Flight Center EMC design and EMC Design and Interface Control Handbook, or shorthand MEDIC Handbook. They specify, and this has been adopted, and certainly in GEVs and many other places, but in this MEDIC Handbook from easily 20 years ago, they talk about making a direct measurement of common mode currents. So if you're talking about a power supply feed or any differential type of interface, you put both wires through the current probe to get your common mode current. And then the inverse of that, if you will, is if you flow one of the conductors, we usually default to the return wire, but it doesn't really matter which one. But you take one of the conductors and put it through the current probe in the opposite direction, so that now you're canceling the common mode and only getting the differential mode current. So the common mode current provides a direct assessment of radiated emissions and crosstalk, and differential mode current provides a direct assessment of ripple applied to the power bus. So they're two different concerns, and you want to know which one you're dealing with. And this differential mode measurement applies to primary power interfaces only. So that, and note that the true differential mode current passes through the probe twice. So what you measure coming out of the current probe is going to be a factor of 2 or 6 dB above the true differential mode current. So we have to take that into account when we're measuring this, that what the current probe is reporting to us is actually twice the true differential mode current. We'll come back to that. But note here that when you do it this way, you're also performing two measurements, which directly gives you the information on the quantities of interest. You're directly getting the common mode current and the differential mode current with the same number of measurements that you've made with the traditional approach, measuring on each individual wire. But if you get an exceedance measure in the traditional type of measurement on the single wire, you'd end up needing to go to these measurements anyway to further diagnose what kind of problem you're dealing with, because the solution to each of these problems is going to be different. So with the same number of measurements, you get directly to the quantities of interest. So there's no additional time to doing this. In fact, you'd argue it's less time, right? You're directly measuring what you're interested in instead of doing an indirect measurement first. So when we talked about compatibility with the power system, and I used a lot of these same charts in the introductory session. So if you participated in that, this should look like review. So I'm representing the power subsystem just as a battery, but that's just an abstract representation of a power system. And you're going to have some common source impedance with whatever conductive connections you use to get from from your source to a distribution point, whatever that looks like. I'm just representing it sort of in the traditional way of bus bars, on the spacecraft, or even in a distribution panel, like in your house or in a building or something. But so you can think of specific examples, but this is trying to notionally show this as an abstraction. Okay, but you go into your common distribution point here with your positive and negative conductors that you're tapping off of. And so you're going to go off you're going to make connections to a load. So we'll call this load 1. And it's going to draw some differential mode current, the intended current for the load to operate the way it's supposed to. And then there will be some, whatever the noise currents are that are riding on top of the intentional DC current to operate the load. Those are what you would call your differential mode differential mode conducted emissions. Now, I just gave away my DC bias here, because mostly what we deal with on spacecraft are DC power sources, nominally 28 volts, which are more like 30 volts, in recent years. But a battery dominated bus where we distribute, let's just say 30 volts DC to all the different loads on the spacecraft. This general concept applies to AC power systems, which are, much more prevalent on the ground, right? 60 hertz, 120 volt AC power distribution. It's the same general concept, but I always show my DC bias because that's most of what we deal with on spacecraft. But anyway, so just trying to keep it reasonably general here, that you'll have whatever your intended current is to operate the load, whether it's DC or whether it's 60 hertz or whatever it is, 400 hertz on some platforms. And then the noise currents riding on top of that are what give you your differential mode conducted emission. So you're not generally hanging only one load off of your bus. You've got multiple loads, and the combined noise currents that all of these loads generate will produce some potential at the distribution point that all loads will see. And so it's going to be that total combined differential mode current times the common source impedance will give you the noise potential. That's what you care about from a power quality standpoint. Okay, so that will be how you define your conducted susceptibility limits. Okay, so differential mode current conducted emissions limits are generally defined for individual loads. I mean, they're almost always defined that way, because if you're testing, you're almost always testing a single box at a time. So you need to define a limit for that individual load. Okay, in terms of voltage or current, we prefer current, and I'll get into that here shortly. But you're defining a load for an individual, defining a limit for an individual load. But for a conducted susceptibility limit, you're generally defining that for the worst case composite voltage ripple at the distribution point. So there's a little bit of apples and oranges going on here, because you're defining your individual limit in terms of current, and then your emissions limit in terms of current, your susceptibility limit in terms of a composite voltage. It's not entirely apples and oranges, and I'm going to go through how we correlate these things, but it's an important distinction, that the conducted emissions limit is for an individual load, the susceptibility is for the composite, everything that's operating on the bus. So we'll get into that right now. So we generally will start, or at least this is my thought process. So we'll walk through this, and then so I'll state this at the outset. I'll get to an eventual answer, if you will, running through this specific example. But what's important is the thought process, not the final result. When I get to a graph at the end, please don't take that as this is what you should use from now and forevermore on every project. That's not the point. The point is the thought process that goes through how to define meaningful limits for your platform, and your mileage may vary. So with that, we'll start with the allowable voltage ripple at the distribution point that all loads will see. And what we typically start with is a 1 volt peak to peak in the time domain. So just kind of across all frequencies, we'll say we can allow 1 volt peak to peak in the time domain. And that's kind of specific to a 30 volt DC type of bus. For 120 volt AC bus, maybe you can allow more. But again, just using our 30 volt DC bus as an example, we'll start with a 1 volt peak to peak in the time domain. So then we want to turn that into a conducted susceptibility limit for a frequency-based conducted susceptibility test applied at component level to provide an upper bound on the expected ripple. So the default per devs, and what we generally apply, on Goddard programs, is a 1 volt RMS limit across the whole frequency range of 30 hertz to 50 megahertz. Okay, now if you actually had 1 volt RMS at every single one of those frequencies and integrated it together, you would probably get something much greater than the 1 volt peak to peak in the time domain. But so this is pretty conservative, but it's generally, I mean, it's our default level that it's not really intended to have that direct correlation, but it's intended to provide a conservative limit that you know, if you can withstand 1 volt RMS at any given frequency across the frequency range, then you have a good robust design. And if you can't withstand that 1 volt RMS, you probably want to know about it. So so anyway, this is our starting point. We're gonna basically take 1 volt RMS across this whole frequency range. Now that's in terms of voltage. So we want to convert this to an average current ripple, an aggregate current ripple using the power bus impedance. Okay, so we say we're going to allow 1 volt RMS across this frequency range here at the distribution point. Well, how does that relate to current? And you just divide that by the common source impedance as a function of frequency. Get into that here in just a moment. That'll be right now, actually. So in the previous session, I went through this general harness impedance model. So it's whatever the connections are that get you from your power source to the distribution point. So I went through the example in the last session of like power distribution in a building, in your office building, in your house, or wherever. The wiring that gets you from the distribution panel to a set of outlets in a section of the building, that's going to have a fairly high common source impedance by the time you daisy chain all those outlets together. Where if you have dedicated wires from every load getting you back to a point very close to the battery, or very or right next to a big capacitor bank, to that will have a much lower common source impedance. But the general concept is that you're gonna, from whatever your power source looks like, you will have some conductive connection to that distribution point. And so you'll have wire resistance or conductor resistance. It could be traces on a PC board, like on a lot of our Goddard internal programs. I mentioned that capacitor bank on a PC board. The distribution point is right near that capacitor bank. And so these connections may well be traces on a PC board, but whatever it is, you'll have conductor resistance, you'll have inductance, and then you'll have your transmission line characteristic impedance at higher frequencies. And so common theme, as I always mention, you have to think about any conductive connection as eventually looking like a transmission line at sufficiently high frequencies. So we can simplify this model where we divide these contributions between the positive and negative conductors. We can simplify this by just combining them all on the positive conductor, just analytically and mathematically. And so we just to look at what this impedance is, we see that we just have our Z naught, our characteristic impedance, in parallel with the sum of R and J omega L. We work through the math, we divide top and bottom by Z naught. And generally, pretty much all the time, the wire resistance is going to be on the order of milliohms, and your Z naught is tens or hundreds of ohms. So this R over Z naught term we can basically set to 0. So we have this expression here, and when we graph this, okay, so when we graph this, we get a general graph that looks basically like this, and I find it helpful. I know not everybody is as much of a mathicist as I am, but when I look at an expression like this, we can simplify this in different frequency ranges to get a better idea of what what is the physical interpretation. So at low frequencies, where you set omega equal to 0, everything cancels out except R. So you have this low frequency plateau, which is your conductor resistance. In the mid-range of frequencies, you basically have the inductive reactance, J omega L. And then at high frequencies, everything cancels out except for Z naught. So this is your general, any harness impedance model basically is going to have this basic shape. And it's just whatever your values of R, L, and Z naught will determine the specific shape, but it's going to have this general characteristic. Okay. And so now we look at different ways of representing this power source impedance. Mill standard 461G specifies a default 50 microhenry Listen. We talked about this last week, but I'm going to review this because this is rather central to all this stuff we're talking about. This 50 microhenry Listen, well, you see it's dominated by a 50 microhenry inductor. Lisens are generally defined by the value of the inductor. So it's called a 50 microhenry Listen. That's how we designate it. So it doesn't even really bother with conductor resistance at the low frequencies. It just doesn't bother with that. So your 50 microhenry inductor gives you the sloped part of the curve here. This is your line inductance. And then the 50 ohm termination of your measurement receiver. These types of Lisens give you a measurement port. So there's just a coaxial connector on the box that you connect a 50 ohm coaxial cable to it and go to the 50 ohm input of a measurement receiver. That provides you that 50 ohm shunt at high frequencies. Okay, so that's what gives you this 50 ohm asymptote at high frequencies. The actual, well, we'll go up here, get into a fuller description of this. This 50 microhenries is intended to simulate the worst case power distribution wiring on large military platforms. Remember, Mill Standard 461. It is a military document for military platforms. So power is generally distributed, or has historically been distributed, as a single wire 5 centimeters above chassis or above the structure on the aircraft or aircraft carrier or whatever it is. And structure is used as the current return path, which we generally don't do on spacecraft. So this type of configuration will have an inductance on the order of 1 microhenry per meter, running as much as 50 meters to the common distribution point. This is all right out of the Mill standard in the appendix to tell you where this 50 microhenries was derived as a standardized inductance to use in these Lisens. This is not realistic for Goddard platforms. Okay, this is definitely one place where doing something just because the Mill standard says so is not appropriate. And it says in the Mill standard right at the beginning, tailor according to your needs. So I've never seen any Goddard platform where this was an appropriate thing to do. And some people have insisted upon it, and that has led to some really interesting discussions. But what I will say is that this type of configuration, in my fundamental sessions, I go through how you can calculate the inductance, capacitance, and characteristic impedance of these different configurations. And this type of configuration that has an inductance of 1 microhenry per meter, the characteristic impedance is going to be on the order of 300 ohms if you just work through the math. So why did they use 50 ohms? Well, I don't know all the ins and outs of it, but basically it enables you to use a 50 ohm system. So I think it's generally recognized that, okay, the real characteristic impedance is going to be something higher than this, but they've just standard to 50 ohms because, 50 ohm measurement devices are what we have readily available, and it is generally sufficient to shake things out. That's the best answer I can really give on that. But just note that this configuration will have a characteristic impedance a little bit higher than this. Now it's a factor of 6. It's not too bad. If the actual characteristic impedance were like megohms, then it would be a different conversation. Now there's an alternate 5 microhenry Lisen specified in the appendix of the Mill standard. Same basic topology. And again, the 50 ohm input of your measurement receiver provides that high frequency asymptote, the high frequency shunt. This may be more realistic. It's certainly more realistic for smaller platforms, but I think it's still overkill for most of what we do at Goddard and just most spacecraft. because we tend to run a dedicated power wire back to the power source, and you're just not going to get 1 microhenry per meter, with that kind of configuration. You only get 1 microhenry per meter when your conductors have significant separation, like 5 centimeters. When you're running a dedicated return wire or set of return wires with your feed wires, the inductance is going to be maybe 1/10 of that. So you might get a few tenths of a microhenry, maybe a microhenry if your power run is very long. But just 5 microhenries is not something you're going to get by accident. I have a picture of the 5 microhenry Listen and I think I showed it in last week's session, that 5 microhenries is just not something you get by accident. So, but we'll get to that if time permits. So on Goddard platforms, the power source impedance is much more accurately simulated by a capacitor network. You have a pair of 10 microfarad feed-through capacitors installed between each power conductor and the ground plane. It's an integral part of the standard setup specified by Mill Standard 462. It's going to be part of the standard suite of equipment that any EMI laboratory that's been around for any amount of time will have these. It's beyond should. They will, right? If they want to be taken seriously as an accredited EMI laboratory, they will have these capacitors. And if they don't, then they should. This pair of capacitors will provide a standardized source impedance at frequencies down to about 20 kilohertz. These capacitors will have if you just work through 1 over j omega c, they will look like about an ohm at about 20 kilohertz. That's where that comes from. Now, for a DC-based power system, like most of what we deal with on spacecraft, we'll add this 10,000 microfarad line-to-line capacitor. You don't want to do this on an AC bus, on a 60 hertz or even a 400 hertz bus, because this will not play nicely in a system like that. Especially these are polarized capacitors, so you don't really want to take that voltage below 0, right? This is only for a DC bus. But this extends that standardized source impedance down to 30 hertz to cover the full range of frequencies specified by the tests in question, the ones that we do per Mill Standard 461. And these 10,000 mic capacitors, they look about the size of a large beer can, or sometimes people say a can of Foster's Lager. But they're readily available and inexpensive. I've bought 3 or 4 of these things over the last several years, and they're readily available on DigiKey or some equivalent for about $100. So, your EMI lab should already have these 10 microfarad feed-throughs, and you can get one of these for $100. As compared to a custom Listen, which I have specified and procured at least one for JWST, was about $10,000. The off-the-shelf, the standardized Listens, I don't recall how much they are, but they're probably a couple $1,000 as well. So, if anybody gripes about implementing this because it's expensive and time consuming, it's not. It's actually much more cost effective than a custom Listen will ever be. So moving right along. So I'm going to work through an example of deriving some meaningful limits using this 5 microhenry Listen example. Now I've said that it's still overkill for most Goddard platforms, but I think it's a useful illustration of how you can correlate limits between differential mode conducting emissions and conductive susceptibility limits. So again, it's the thought process more than the final answer that I want you to keep in mind and take forward. So note that when you use this, as I mentioned in the last session, the Listen can be line impedance stabilization network or line impedance simulation network. If it has, we'll go back to the okay, here we go, right on this page here. If it has a topology like this, where it's specifying the differential impedance between the positive and negative leads, then it is more of it is a line impedance simulation network. These default 5 microhenry Lisons, going back to the schematic here, this is actually specifying an impedance between the individual lead and the ground plane. So when you're using when you're using a stabilization network, you need one on each power lead. So I'm kind of taking some license here. I'm representing this more as a line impedance simulation network here, and I may want to update these charts to minimize that confusion. I'm just kind of seeing this now. It's specifying this impedance with respect to the chassis, with respect to the ground plane. So you need 2 of them. You need one in series with each power lead. Okay, is that clear? I want to make sure that point doesn't get lost.
Another thing the Listen had the standard Listen has is some capacitance to the ground plane.
Yes, if we go back here, yeah, there's a capacitor between the input feed and the ground plane. That has a similar function to just our basic capacitor network. It's the same general idea as decoupling your power source, like at an IC, where you put a capacitor at an IC. I mean, we call them decoupling capacitors because you want whatever instantaneous current feed the device is drawing to come from that capacitor rather than directly from the power source over that, whatever impedance that feed has, right? You don't know how far away your power source is. So this capacitor is decoupling you further from the actual impedance of your power source. So
John, so that's basically returning the noise to the source, right? AC noise goes through that capacitor back to the source and doesn't pass through to your device under test.
Yes, correct. But the other benefit, or one of the other benefits or impacts of that is you can use basically any garden variety DGSC power supply to run your tests. That with a properly designed Listen or with our capacitor network, the source impedance that your EUT sees is what you put here, and it decouples you from whatever source impedance your power supply has, and that's very significant. You don't have to worry about spending a ridiculous amount of money on a power supply with some very stringently low source impedance. When you put a Listen or the capacitor network in place, it decouples you from that, and the EUT sees the source impedance of your Listen or capacitor network that you're putting between them. Okay, all that clear? Okay,
Yes.
so let's continue here. So you're putting 2 Listens in place, one in series with each power feed, and given the caveat, this is effectively what the source impedance looks like. I'm just going to assume about 50 milliohms of series resistance on each lead here, so a total resistance of 100 milliohms, even though that's not in the Listen. So again, just for the sake of an example here, and here again, if somebody specifies a Listen like this, just think about the implications of that. If your spacecraft has a total current draw of, say, 50 amps, I think 100 amps is I think fairly typical, and that's actually the example I'm going to use here. So sure, I'll go with 100 amps. And on a full up, fairly large spacecraft, you might have 100 amps of total current draw. And remember, this is the impedance at the distribution point. So all the current to all loads is passing through this impedance. So if you have 100 amps passing through 100 milliohms, what kind of voltage drop does that give you at the distribution point? That's 10 volts. Are you actually going to allow a 10 volt drop on a 30 volt power bus DC? Probably not. So it's all the things to look at when somebody is specifying a Listen in an EMC control plan or something like that. pay attention to stuff like that to see how much thought they've put into actually defining a meaningful impedance. Now, again, it might be for worst case and all that good stuff, you know, and that's all fine if that engineering thought was put into it. But sometimes I think some very unrealistically high numbers are put into these limits. So it's just something to pay attention to. So we're going to assume this resistance of 100 milliohms, and then our 5 microhenries, which is going to be a total of 10 microhenries, right? And then 100 ohms is our going to be our combined impedance because of the pair of 50 ohm resistances here. So here again is our general shape here, but now it's formed by 100 milliohms, 10 microhenries, and 100 ohms up top. So we take our conductance susceptibility limit, our desired default limit of 1 volt RMS across the frequency range from 30 hertz to 50 megahertz. Again, typical. Sorry, is there a question?
Yeah, I just had a question real quick. So, we're doing 2 listens on the one on the source and one on the return. So that works for single point ground. What if we did do a chassis ground? Will that make a difference, or the return go to the plate instead?
A chassis ground where?
Chassis ground in the spacecraft, but we don't do that right now. We do single point ground. But if we did, I mean, that would then when you would ground it to the ground plane of the bench, right? Instead.
If you were using kind of the more traditional approach of I'll say right now that this starts to get into the weeds, and I'd rather defer this to maybe a private discussion. But I'll give you a quick answer here that if you're using a traditional approach where you do indeed have a single wire going to a load, and then you're just using structure as your return path, like on a military platform, then just using one wire, one lead going through one listen that's terminated to chassis is probably a better representation of that type of power distribution. Right. If you're using the structure as your return path, and then like that's your single point ground here back at the power source. But if you're using 2 wires, if you're using a dedicated return wire coming back to your power source, and even if you're connecting that negative lead to chassis back here at the power source, this is still what you want to do, because you still are going to have that impedance of that return wire above the ground plane. So
Okay.
Does that help? Yeah.
Yep. Thanks.
Okay. All right. So again, just working through this general example, if we take our CS limit of 1 volt RMS from 30 hertz to 50 megahertz, then we divide that. You know, it's a constant 1 volt level. Again, remember it's RMS, but we're taking this constant 1 volt level. We divide that by this source impedance. You know, and I just did this in Excel. It's easy enough to do. So you just divide 1 volt by that source impedance. So you get an allowable aggregate current ripple that's going to have the inverted shape, of course. Okay. So you're allowing, in this example, you know, 10 amps, basically DC or low frequency current. And then it goes down to about 10 milliamps above a few megahertz. So that is our aggregate current ripple that we're saying that's what we're allowing at the distribution point. So now we want to apportion that to each load as a function of current on a per ampere basis. We usually default to a minimum of 1 amp. So you can default or kind of standardize it to a 1 amp load, which is fairly typical for any moderate sized electronic box. You know, some boxes are going to have a little more, but just start with normalizing it to a 1 amp load. So you divide that curve, divide that allowable aggregate current ripple by the total current capacity of the bus. Now I'm going to use 100 amps as an example. That is, you know, in the ballpark of what a lot of our spacecraft use. Plus, it makes the math easier. So we just take this, divide it by 100 amps in this example. Then we want to convert it to dB microamps for a component level true differential mode limit. But then remember that when we make a differential mode measurement, the current, the actual true differential mode current is passing through the current probe twice. So we add 6 dB for a differential mode measurement. That's the way we do things at Goddard. If your test system is able to add a 6 dB factor into your measurement software to account for it there, so much the better. But you need to account for that 6 dB factor somewhere. And we generally just find it cleaner to just acknowledge that the measured level is going to be 6 dB higher. So we just move the level up by 6 dB. Okay, so when you go through the calculation prior to the 6 dB, you get this red dash curve. Then we add the 6 dB to say this is what our apportion differential mode limit is, which is the true limit plus 6 dB. Then that's normalized to any load with a 1 amp DC current draw. So you would just add 20 times the log of your steady state load current. So, you know, if it's a 2 amp load, you would add 6 dB to that and so on. But that this level specified for a 1 amp current draw should work in the majority of cases. And then you can adjust it as needed for higher current draw loads. So again, your mileage may vary. It's the thought process and the methodology that I want you to take with you more than this answer. Much more than this answer. This is just for this specific example that we walked through. This may well work, you know, in a large number of cases, but this is the sort of thing to pay attention to see if you're, you know, if you're being given limits that actually make sense, or if you're having to define limits, right? So, okay, so getting into some of the test methods here. So the mil standard 461G CE 101 test method. That's the lower frequency portion. So from the default is 30 hertz to a 10 kilohertz. It specifies a current measurement. Okay, so with a current probe, the default is around each lead one at a time. Okay. And then CE 102 is the higher frequency portion, 10 kilohertz to 10 megahertz, specifies a voltage measurement across a listen. Okay. This is definitely a point I want to hammer home. This is something you need to take with you. If you specify CE 102, this is what it means. You are specifying a voltage measurement out across a listen. This is why the listen provides that measurement port so that you can connect a coaxial cable. Wait, I'm sorry, that's going to be UT. There's your measurement port. And, you know, with some attenuator, right? When we get into the lab portion, we'll talk more about that. But you can hook up a coaxial cable to that, you know, to that coaxial connector and go to your measurement device to measure the voltage directly coming out of the listen. If you are specifying a current measurement like we do in GEVS and at Goddard, it is not CE 102. I see this all the time in test plans where they'll say a tailored version of CE 102 that's actually a current measurement. Please don't do that. And if you see that in a test plan, flag it and say, don't call it CE 102 if you're making a current measurement. This is one of the points that I made last week when we talk about nomenclature and speaking the language. You know, if you say it's CE 102, you mean a voltage measurement across a listen. And if you're doing anything else, it is not CE 102 and should not be called that. It may sound picky, and I don't care because, you know, wrong is wrong. You know, when you speak, you know, when anything like this that you say to EMC engineers means a certain thing, and it just causes confusion. Much more than the time it's taking me to go through this now. I've seen many discussions just swirl and swirl and swirl when people are not using the right nomenclature. So, but more back to the technical point. is voltage measurements will depend significantly on the power source impedance, which can vary across platforms. And I'll show you the impact of that when we get to the lab session next week. So in the GEVS test methods, we prefer differential mode current measurements, as I've just talked about, but across the feed-through capacitors instead of Lisons. Okay. This will provide a worst-case measurement of current emissions that is largely independent of the source impedance. The idea here is that this capacitor network is intended to represent a battery to the best extent possible with, inexpensive capacitors, relatively speaking, as opposed to putting a real battery there, so that whatever noise current that your EUT wants to draw at any given frequency, the battery simulator will be able to provide. Essentially, that's the general idea, without limiting that current. You want to get an idea of what is the EUT going to draw as a worst case, out of a very low source impedance. So okay, so different current probes are required for different frequency ranges, but so in this scheme of things, CE 101, we will extend the upper limit to 150 kilohertz, and this is actually part of tailoring guidelines in the mill standard, by the way. The default that I mentioned earlier is the upper limit was 10 kilohertz, but we will extend the upper limit of CE 101 to 150 kilohertz, and then we will use the old. I hate saying old because that makes it sound bad, but the traditional CE03 test method from mill standard 462, tailored for differential mode from 150 kilohertz to 50 megahertz. So if you're doing a current measurement, call it CE03. Do not call it a tailored version of CE 102. So other than the different current probe used for the different frequency ranges, CE 101 and CE03 are essentially identical. So here's the general setup diagram for mill standard 461G, figure 2. The current probes will be placed near the Lisons if you're doing it, if you're doing CE 101, that is. And then if you're doing CE 102, the voltages are made at the Lison port. And you'll just connect up your coaxial cable here and go straight to your measurement device. So in the one sense here, if what you're really concerned about is voltage, and I get the general principle here, right? I don't want to sound like I'm disparaging CE 102 too much. I get the general principle that what you're really interested in ultimately is voltage ripple. That's what every device hooked up to a power bus is going to be concerned about. That's what it's going to see. It's not going to directly see or care about the current draw from some other load on the bus. What it's going to observe, what it's going to potentially impact you as a user on the bus, is the voltage ripple at the distribution point. So the general idea here is you can directly measure that. You can measure what are the direct voltage emissions that are going to be at that distribution point. But that's predicated on this being a representative source impedance. If this is unrealistic, then the measurement you get here is going to be in question, and it sort of meets the purpose, right? You want to get a reasonable or representative measurement. So the general setup for GEVS, this is our modified version of that diagram. The main thing is that we replace those Lisons by a capacitor network. Okay, and then again, we still place our current probes near the capacitor network. So here's some representative photographs. We like this Pearson 3525 current probe at the low frequencies. And you can see the negative lead is running through the current probe in the opposite direction for differential mode measurement. And then the higher frequency portion is this electrometrics current probe, and might be a little hard to see, but here again, the one of the leads is running through. So yeah, it's the red lead here. It's running through the current probe in the opposite direction as the positive lead. So little bit more on these limits. So if you look in the appendix of the mill standard, they give you a little more information about how to define limits for a 5 microhenry listen. The default limits in the main part of the document are for the 50 microhenry listen. So we generally use curve 2 for, well, a 28 voltish DC bus. So, you know, where it says 28 volts, okay, 30 volts is essentially the same thing. So we're using curve 2 as our starting point. And so here again, this low frequency plateau scales with load current. I didn't make that up. This is right out of the mill standard that below 2 kilohertz, the limit will scale is 20 log of the steady state current. When you look at the CE 102 limit, mill standard, and I know that I generally don't like to use this, but I'm going to walk through this to illustrate how these limits correlate with each other, you know, by design. We take the CE 102 limit and the 5 microhenry listen impedance, because if you're doing CE 102, you are using a listen. So using the 5 microhenry listen example, at 150 kilohertz, the starting frequency of the 5 microhenry listen, the impedance is right around 5 ohms or 14 dB ohms, just 20 times log of 5. So 14 dB ohms. The limit, the CE 102 limit at 150 kilohertz is about 70 dB microvolts. So we take B equals IZ, right? But in dB space, subtraction is the equivalent of division for numeric quantities. So to get the equivalent current, we take our 70 dB microvolts, subtract 14 dB ohms. That's equivalent to dividing by the impedance. And that's 56 dB microamps. Well, lo and behold, that is the limit at 150 kilohertz for CE 101. This is by design, definitely not by accident. So that when you're using the 5 microhenry listen and you're going to apply CE 102, the limits line up, right? The limit of CE 101 lines up with where CE 102 picks up when you do this correlation. I mean, that is not by accident. And looking at the old CE03 limit, lo and behold, the limit at 150 kilohertz is 56 dB microamps. So again, the people defining these limits did their homework. They made sure that all these pieces line up. So applying this to our approach here, to at least in GEVs, and in the low frequency end, the CE 101 frequency range, 30 hertz to 150 kilohertz, we have this family of limits. Our starting point is the limit for 1 amp and below, but we add 6 dB to the limits that we just looked at on the previous page. So at the low frequency plateau is 100 dB microamps. So we add our 6 dB to that for true differential mode measurement. So it's 106 dB microamps, and otherwise has the same shape. So that 56 dB microamps at 150 kilohertz now is 62 because of the 6 dB factor. And then for higher current draw loads, we increase the low frequency plateau. We keep the 62 where it is at 152 kilohertz, but we increase the low frequency plateau. Sometimes I kind of wish I hadn't drawn the curve this way because it's not intended to be, you know, discrete steps, right? Or I mean, you could do it in 1 amp increments, you know, if you wanted to, but it's not like you go up to 3 amps. If you have a 2 amp load, then your limit should be, you know, in between these, right? But then at above 150 kilohertz, we pick up, you know, at this point at this 62 dB microamps. And we basically take that CE03 default limit and increase it by 6 dB across the board. So this is our default limit in GEVs. And I just want to show you where all of that came from. These limits didn't just, you know, come out of the blue. So, and they come right from tailoring guidelines in the mill standard. And I mentioned the low frequency plateau shifts with load current. The low frequency limit extends out to 150 kilohertz instead of 10 kilohertz. And we already went through here. The limits are intended to coincide with the CE 102 limit at 150 kilohertz based on the 5 microhenry limit. So, and we talked about those points. So we look at this example apportioned limit versus the default GEVS differential mode current limit. The limit that we derived, in the previous discussion is shown here in the red curve. And the default GEVS limit for a 1 amp DC current draw is what's shown here. So at the low frequencies, lo and behold, they line up very nicely. At high frequencies, the default limit is a bit more stringent, but if you do this kind of homework up front, then you may be able to define a less stringent limit at the higher frequencies here, and that's easier for your equipment to meet and set yourself up for a lot fewer waivers, right? So just if you do this homework up front, then you define a meaningful and self-consistent set of limits across the board that then you really understand what you're dealing with and any potential effects of an exceedance are. When you just apply the default limits without putting this engineering thought into it, then you don't really have any basis for assessing exceedances. Can you waive something, or is it actually likely to cause a problem? So a few words about the frequency range. Each unit on the bus generally has a switching DC to DC power converter. Again, your mileage may vary, but that's most of the time what the power bus and what your power distribution wiring is going to see first, or whatever filtering is in front of the DC to DC power converter, but that's generally what it's seeing. So the raison d'etre of a DC to DC converter is to sample effectively the power input at a switching frequency, typically in the order of 100 kilohertz and above, anywhere from 50 kilohertz to maybe 500 kilohertz. Again, your mileage may vary. And then provide regulated stable DC voltages required by the circuitry in the unit, whatever, +5, plus minus 15. Again, showing my age for digital logic, I always default to +5. Seems like that's almost never used anymore. It's 3.3, 1.8, 2.5, whatever, but you get the idea. So the DC to DC converter control loop, it generally addresses the low frequency ripple. So if you're sampling at 100 kilohertz, but you're down at the low end, you've got some 30 hertz ripple there. Well, that sampling action, I keep meaning to put together a little diagram to illustrate this, but bear with me, I'll go through it in words. But you're sampling, this 100 kilohertz effective sampling of that level. You're oversampling the noise contribution of anything at a much lower frequency, and so that control loop, the pulse width modulation, it will adjust to give you the desired voltage you want at the output, to adjust for whatever low frequency variations happening on the input side. That's one of the entire points there. So we generally don't have a whole lot of susceptibility problems at low frequencies for this reason. That's what the power converters are designed to do. Now, high frequency ripple is addressed by the input filters. You generally got a pretty healthy bank of capacitors, probably some inductance in front of them. And so high frequency ripple generally isn't much of a concern either. Your filter capacitors knock that out, and your converter just never even sees that. So the real concern, conducted susceptibility issues, tend to occur more at the mid-range of frequencies. So kind of between the effectiveness of these two factors, of the control loop and the high frequency filters. Just a little word to the wise going forward. Okay, at this point, we get more into the laboratory things that I'll cover next week. I'll just give you a little sneak preview that our equipment under test for all the little demonstrations I'm going to do is this interpoint converter that I got from the power group here in my building at Goddard. And notice the complete absence of any filtering in this thing. That's by design or by lack of design, I'm very proud to say. I intentionally wanted a noise-making thing, and that's what this is. And so there's no filtering on it. It's not even in a shielded enclosure. It's just a plastic box that I had lying around. And so that's when we get into some of these lab demonstrations, this is going to be our guinea pig, if you will, or our representative equipment under test. And then you see these listens over here that we'll use for the start of the demonstration. All that stuff will go through next week. But I think one thing I do want to show you is this listen, and then we'll switch over to common mode. It looks like we have about an hour, so doing okay for time for people who can hang on to 11 o'clock. But yeah, okay. So this is our pair of 5 microhenry listens in line with the power feed. So this is just an old workhorse power supply. But as I said, with the listens or the capacitor network in place, you don't really need to care too much about the specific qualities of your power supply, right? As long as it works and gives you a stable output, you run it through your listens and so on. But if you open up one of these listens, one of these 5 microhenry listens, that's what you see. That is about actual size, actually. If you've got a reasonably large display, you know, that whole inductor there. I mean, the 5 microhenry listen is dominated by that 5 microhenry inductor, you know, right there, and that's about the size of my hand, give or take, and that's 5-6 inches long, and I think that's a 3-inch piece of PVC pipe. And so you got the 1 microfarad. It might not be exactly 1 microfarad. The specific values of these capacitors isn't all that important. The 5 microhenries is the crucial thing. So you have these capacitors to chassis, and then, but the point I want to make here, and then we'll continue this part of the discussion next week, is this gives you an idea of what it takes to get 5 microhenries. Right, there's essentially no such thing as 5 microhenries as stray or leakage inductance, right? To have this multi-turn coil around a 3-inch piece of PVC pipe to give you 5 microhenries, you need to mean it. And then the 50 microhenry listen is even more significant. It's about a foot long over I think a 4-inch piece of PVC pipe, and the chassis is about a good twice as wide and about half again as long, something like that. But the 50 microhenry listen is big. So to get that kind of inductance, you have to mean it. Like you're talking about widely separated conductors running for a very long over a very long distance, and that's just not what we have on spacecraft by and large. You know, you have your return lead is twisted with the send lead. So your resistance, your inductance per unit length is much lower than a microhenry per meter. It might be tens to maybe 100 nanohenries per meter. So over a very long run, and for over on a spacecraft, a very long run is probably on the order of 10 meters, not 50 meters. You know, so you might have a microhenry or so. So just giving you an idea, if you've never worked with a listen, if you've never opened one up, this is what it takes to get 5 microhenries. And so it just gives you an idea of what inductance is if you're not as familiar with it, right? And kind of similarly, I'll just mention with capacitance, like microfarads of capacitance is also something you don't get by accident. Like you need to mean it. You need a physical capacitor. Stray capacitance, leakage capacitance is more on the order of picofarads, tens to hundreds of picofarads. Even a nanofarad is kind of hard to get by accident. But I think it's just helpful to keep that sort of thing in mind, that if you're troubleshooting a problem, and if you're doing some calculations or what have you, and you need many microhenries of inductance to explain what you're seeing, then you're probably not dealing with stray inductance, and that's probably not a working theory if that's what you're thinking it is, right? Like, oh, there may be some leakage inductance that's messing with things, and if your calculations show that you need 5 microhenries or more to explain what you're saying, that's probably a theory to abandon and look for something else. Okay, so with that, any questions on differential mode? Because now I'm going to shift gears and go to common mode. Anybody still there?
Carry on.
Yep.
Okay.
Hey, John, just a
Okay.
quick, are you posting these charts somewhere?
Yes, of course. The same folder that I put last week's in, along with the videos, I'll put these in that same folder.
All right, can you put a link in the chat?
Yes, well, I'll
Thanks.
put it in an email that I send out when we're done here. Yeah.
All right, great. Thanks, John.
Okay, so first several charts here, because I split this up into 2 different talks and decided kind of last week to match them together. There'll be some repeat that I'll be able to skip over, but here, this is a review from last week that interconnecting cables are very much a part of your equipment under test. That common mode energy can couple to these cables, which then can and will radiate. Conversely, radiated energy can couple to the cables, which can then couple back into your U-tube. So you need to come to an EMI test with representative cables. There's no such thing as a box-only level EMI test, unless you're talking about something like a cell phone that's not plugged into a charger, but that's almost never what we're dealing with, for spaceflight hardware. And if you shortchange the box level test, you're only inviting additional risk at higher levels of integration, thereby negating the entire purpose of your test. So don't do that. Okay, so when an EUT meets RE and RS requirements on a military platform, there's generally a low risk of crosstalk. The default RE102 limit corresponds to common mode current levels on culprit cables that are too low to pose a significant crosstalk risk. So RE limits, which are RE102 limits, which are by definition to protect radio reception, are inherently significantly more stringent than what is necessary to protect against crosstalk. Outside of radio bands, the default limit may be relaxed, and this is precisely the reason that RE102 exceedances have historically been the largest sources of waivers on many Goddard platforms. Where outside of the frequency range of a known radio receiver, the limit is fairly arbitrary. So if it's unnecessarily stringent, we grant waivers for exceedances that are tens of dB above the limit. And that's the sort of thing that has led to Rodney Dangerfield being our patron saint, which is something I'm trying to counteract. Nothing against Rodney Dangerfield. I love his humor, but there we are. But most Goddard platforms do not use antenna connected receivers below 200 megahertz. So following this guideline, we generally apply RE102 only above 200 megahertz. If you do have a radio receiver operating below 200 megahertz, then by all means you need to apply it. But if not, we started above 200 megahertz, and I'll discuss the significance of that frequency here in just a moment. So the dominant concern below 200 megahertz is cable-to-cable crosstalk. And as I love to quote the late great Henry Ott, conducted emissions limits are really radiated emissions limits in disguise. So a word about the RE102 test method. One of the significant things to point out, this is right out of the mill standard, by the way. This is a figure in the RE102 section of the document. When you're doing RE102, the test antenna is placed 1 meter from the test setup boundary. I'll have a bit more about this when we go into the specific RE102 section or session. But it has to do that the antennas are calibrated for a distance of 1 meter because you are very much in the near field. Okay, so again, I'll go into further details in the later session, but this is a non-negotiable when it comes to RE102. You're placing the antenna at 1 meter from the test setup boundary. And we have these different antennas that we use in different frequency ranges, just like different current probes suited for different frequency ranges. So there is an antenna configuration break at 200 megahertz. So that's one of the significant factors for that being our break point where we do RE102 only above 200 megahertz. So that doesn't mean we don't care what's going on below 200 megahertz. we're just going to look at it a little differently. So the dominant concern, below 200 megahertz, is cable-to-cable crosstalk. So RE 102 and RS 103 do not effectively address this concern. As we just talked about, RE 102 specifies a 1 meter measurement distance. I've never addressed a crosstalk problem where with cables that are separated by 1 meter or more. I mean that's just not really the concern there. Crosstalk risk is most significant for cables that are much closer together than that, on the order of a few centimeters. So any attempts to correlate measured field at 1 meter to an expected field at a few centimeters is non-trivial at best, and it carries a very large uncertainty. It's just, you know, in the near field, things are very, very chaotic, as it were, or it's just very, very difficult to get a meaningful prediction or meaningful assessment of what's happening at a distance of 1 centimeter from a measurement at 1 meter. It's just not a worthwhile thing to do. So this sort of thing is much more efficiently addressed with direct measurements of common mode currents on cables. So a direct measurement of common mode conducting emissions from your culprit cables, and then using the CS114 test method, and I've got a whole session on that, fear not, to assess common mode conductive susceptibility on your victim cables. So getting back to Kirchhoff's current law, okay, we went through this earlier, so let's get through all this. And now we're going to talk about common mode currents. So again, we talked about the traditional measurements on a single wire, and then common mode, direct measurements of common mode and differential mode currents. And my apologies, that's all repeated. Okay, so here's some new stuff here. So when we look at capacitive or electric field crosstalk, that is related to the voltage, the potential on a culprit conductor, culprit wire. So you'll have some victim circuit nearby. You know, they talked about in my fundamental session on electric field potential and capacitance. Well, any two conductors that are in any proximity, or well, any two conductors that don't have a conductive connection between them will have capacitance between them. It's just a matter of degree. And so the reactance, our capacitive reactance is the well-known 1 over j omega c or 1 over j 2 pi fc. So you'll have some reactance associated with this capacitance here. Then our total victim impedance is going to be the combined parallel impedance of the two impedances on either end of this conductor. So there's the parallel impedance of Z1 and Z2. So you set up an impedance divider here. So the potential coupled onto your victim is just going to be the potential on your culprit through this impedance divider. Okay. Now, one of our biggest mitigations against capacitive coupling is shielding. Because what that's doing is that now, instead of having a capacitive path to a nearby victim conductor, that capacitive path, the first thing that any capacitive, any leakage capacitance is going to see is the shield conductor. Right. And so again, per Kirchhoff, or as Kirchhoff reports per Mother Nature, that current will get back to its source. It must get back to its source. So it sees this path long before it sees, you know, any other victim conductors. It sees the shield, and so that current will make its way back to the source using that path. Now, it probably isn't going to get all of it. There's probably still going to be some energy, some net common mode current that's not fully, you know, taken back to the source through that shield. So there some residual capacitance will provide a path for some additional current to go in this direction. But if you put another shield around your victim, then that energy will find the shield first and then use that path to get back to the source. So the important thing is that the shield is providing a low impedance path for noise currents to return to the source. It's redirecting the noise currents. It's not making them go away. If you're making them go away in the form of reducing how much crap your source is emitting, then you don't need the shield. But if I'll keep using my technical term crap, but if the source is still emitting crap, then if you determine that mitigating that, or minimizing how much noise the source is actually generating, if that's prohibitively expensive or time consuming, well, if you can add shielding to both your culprits and your victim, but just know that you're not making the noise go away, you're just redirecting it. And that's okay, as long as you realize that's what you're doing and you're doing it effectively. Now, we do have a way of measuring common mode potential on a culprit wire. We have this Fisher CVP1 capacitive voltage probe. We do have one of these at Goddard. We do use it occasionally. And if that is your concern of common mode potential on a victim cable or wire, you can use this. But there's a more efficient method. I'm not really going to spend any time talking about this. If we look more at inductive or magnetic field crosstalk, we'll take, and we have a culprit conductor above some grounding conductor. This could be a ground plane or it could be a wire, but so we're just going to keep it general here. But whatever current that you have on that culprit will generate some magnetic flux around it, per the right-hand rule. Point your thumb this way, wrap your fingers around this way. It'll generate some magnetic flux density, or B field. The total flux through this loop will just be the surface integral of that magnetic flux vector through that surface, through the loop. And the inductance is defined as the total flux divided by the current that caused it. And so this is the partial self-inductance of your culprit conductor with respect to the grounding conductor. Okay, inductance is always defined in terms of a loop. So it's the flux through this loop generated by the current on that culprit conductor. Now you put a victim, your victim conductor, so just some other wire in proximity to this, let's say in the same bundle, or generally we're talking about composite cables here. But whatever current is on that victim, so for the moment, we're going to pretend that this is just an isolated conductor over this same ground plane, just for the moment. Then we'll start talking about the interactions between these. But the current that's generated on that victim conductor will also generate some flux. Now, again, using the right-hand rule, the flux is going in the opposite direction. But the total flux, again, is the surface integral of that B vector for the victim current. And so now you'll get this partial self-inductance of the victim conductor with respect to that same grounding conductor. So due to the similar geometry, if we said that these are cables or wires in the same bundle, then they'll basically have the similar geometry with respect to the grounding conductor. So we can say that these inductances, the self-inductances, are essentially equal, the first order. Now we go back to the interaction between these things. All of the flux from your culprit conductor will couple into the loop formed by the victim conductor with the grounding conductor. So what's the significance of that? Well, we're getting to that. So per Faraday's and Lenz's law, this flux will induce an EMF or a potential in the victim loop to oppose or impede the incident flux. And so that coupled potential is going to be the negative time derivative of that flux, just dP/dt. And just the negative sign, significance of the negative sign is that potential will be oriented so that it will impede the incident flux. So you point your thumb in the direction of the counter flux that will impede or oppose this incident flux, then your fingers of your right hand wrap in the direction of that coupled potential. So if you're doing any analysis or calculations based on this, once you've defined your coupled potential source or your victim coupled potential in this, you define the polarity of this source this way, with the positive side going that way, you've basically addressed the concern of the negative sign here. So for any further calculations, you can essentially drop the negative sign. But always keep the negative sign in mind so that you know how to define the polarity of your source. Okay. So the mutual inductance of our culprit current into our victim circuit is that culprit flux from our divided by our culprit current. Okay. And our victim potential is, we can write that as this mutual inductance times the time derivative of our culprit current, or in the frequency domain, J omega times the mutual inductance times the culprit current. But because of the similar geometry here, we can say that this mutual inductance basically equals to first order. It's the same as the self-inductance of each of the culprit and victim loops. Everybody clear on this? I've seen this sort of thing just sort of mentioned in passing in some textbooks that, well, of course, the mutual inductance is the same as the the self-inductance of either your culprit and victim loop. And they didn't go through all of this, and he was left wondering, okay, how can we draw that conclusion? So when I reasoned through this for myself, I'm like, okay, now I understand this. Now I understand this statement that the mutual inductance between these circuits that you're defining to be conductors that basically have the same geometry with respect to a ground plane, that's how you can draw that conclusion, that this mutual inductance is approximately the same as either conductor self-inductance. Everybody clear on that? And that's an extremely important point. Okay, I'll take that as a yes. I'm hoping people are still listening. So the mutual inductance to a nearby victim conductor will induce currents on it. Most likely why it's called inductance. So it's a bit like a transformer. In fact, it's exactly like a transformer. I mean, we represent mutual inductance basically the way we represent a transformer in a circuit. So if we just look at this mathematically, so if we look at our coupled current, remember that magnetic flux induces a voltage. Sometimes we erroneously say it's inducing a current. It indirectly induces a current, but the thing it's directly inducing is a voltage. The V is minus d phi dt, the negative time derivative of the flux through the loop. The induced current is the current in the victim loop is a function of that induced voltage divided by the impedance of the loop. So it's going to be dominated, at least at higher frequencies where this sort of thing is happening, it's going to be dominated by the self-inductance of the victim loop. Okay, so we've said that our induced voltage is minus j omega times the mutual inductance times the current. Well, the impedance of our victim loop is going to be dominated by the self-inductive reactance, so j omega LV. A bunch of these terms cancel. We've said in the previous slide that the mutual inductance approximately equals the self-inductance of either loop. So these terms cancel. So in the worst case, the victim current can equal the culprit current. In many cases, it's probably going to be a little bit less, but in the worst case, we can and should assume that the current can be about the same as what's on the culprit. And that's going to be true even if there's some separation between these conductors, I mean, to first order. So it's generally best to assume that the coupled current is going to be, in the worst case, can be equal to the culprit current. Okay. So inductive crosstalk may be directly and efficiently addressed with measurements of common mode currents on cables. And this gives you an apples to apples comparison, right? So we can directly measure common mode emissions to determine, what any culprit is emitting. And then we can directly apply, a signal to a victim cable to determine what is its threshold of susceptibility. And we can do both of these measurements with clamp-on probes. We use a clamp-on current monitor probe for emissions. And I'll show you these in the lab next week. And we can use a clamp-on current injection probe for susceptibility test. Now, notice that in general terms, these are very similar devices. Right? They look a little bit different, but it's really just size, right? But they both have a magnetic core, and then there's a coil of wire wrapped around the core. So the monitor probe is, where you've got the current carrying conductor going through it. You're not directly measuring current, you're measuring the magnetic flux that the current is generating. So the magnetic flux is going to be captured in that magnetic core, and then that will induce a potential in the coil of wire wrapped around the core. These are sometimes called current transformers, because that's exactly what they are. They're behaving as a transformer. The primary is formed by the loop of the conductor you're measuring with respect to the ground plane, and the secondary is just the coil of wire wrapped around it. And then the injection probe works basically in reverse. You apply a signal here, and then it's driving a signal to that coil of wire around the core, and it's inducing a magnetic flux through the core here, and then this wraps around your cable under test, and so it's generating a magnetic flux through that loop between the cable under test and the ground plane, which induces a potential, and so on and so forth. And I'll get into that, a lot more details of that when we talk about the CS114 test method, which is what this is used for. But the big point here is no disconnections or reconnections are needed with these clamp-on probes. So when you hear anybody gripe, oh, nobody gripes about this stuff ever. But if anybody says, oh, these tests are so time consuming to perform, well, no, you don't have to disconnect anything. You don't have to, demate or disturb any flight mates. The probes just, they clamp open and clamp around the cable under test, and away you go. And the measurements may be performed in the development lab before you ever even come to an EMI lab. And I highly recommend that. If you engage your EMI lab, our EMI lab has a remote setup where they could come and actually do measurements for the record with calibrated equipment and so forth. They can come to your lab with appropriate notice and arrangements and do runs for the record if you so choose. But even apart from that, it's very straightforward to make measurements like this, at least as early diagnostics, which I highly recommend you do. These are very simple measurements to make. We're happy to come show you how to do them. And they're really good, effective diagnostics to perform even at board level before you even put a box together. So the default common mode conducting emissions limit in GEVs is a flat level of 50 dB microamps we generally start at 10 kilohertz. If you really are concerned about low frequency currents, which might be driven by magnetic concerns, like low frequency magnetic concerns, you can extend the limit down to 30 hertz. But generally speaking, starting at 10 kilohertz works for most missions that don't have low frequency magnetic concerns. So below 30 megahertz, we basically use the modified CE101 and CE03 test methods we talked about before, where for differential mode, you're wrapping one of the conductors through the current probe in the opposite direction. For common mode, for your power leads, they both go through in the same direction. And for signal leads, for signal bundles, it's just around the entire bundle. So again, you're not perturbing any cables. Sometimes I get the question that I think people interpret this as we want to go in and measure the common mode current on every conductor or every twisted pair inside a bundle, and that's not what we're after. We're looking for the composite common mode current of a cable bundle, or and I should clarify what that means. You might have 4 or 5 cables, individual shielded cables that are tie wrapped together in a bundle on the spacecraft. Ideally, we would want to make a measurement of each individual cable, but each cable assembly, not where we're not looking to perturb your overall shield or your overall jacket or any of that stuff. It's just an overall cable assembly. We want to determine what are the emissions on each individual cable. And so one of the big advantages that gives you is that now you know which cable has the emissions, as opposed to a radiated emissions measurement where all you know is that something that the antenna is pointing at is making noise. When you make a measurement like this, then you know exactly what cable and what interface is causing you the problem. And then you can get that much more quickly to diagnosing and addressing it. So at higher frequencies, there's an alternate method using this device called an absorbing clamp. And I'll talk a little bit more about this coming up as time permits. So just a little bit more about the nature of crosstalk. So when you talk about inductive crosstalk into a loop, your induced EMF is the time derivative of the magnetic flux. So for an electrically short cable to first order, we can assume that that the magnetic flux is constant over the length of the cable. And also to first order, I'm going to assume that the magnetic flux is constant over this direction. Clearly that's not true. The analysis gets a little more complex, but to first order, we'll just assume that the magnetic flux is constant in the vertical direction. And if it's an electrically short cable, where when the cable is much shorter in a wavelength, we'll assume that it's also constant in this direction. So when it's constant, we can just say that the total flux is just the flux density times the area. But when it's an electrically long cable, then the magnetic flux is varying along the length of the cable, so we have to take an integral. We'll still assume that it's constant over the height. My apologies, I don't have it labeled here. The height, h is the height above the ground plane. But we're going to integrate that magnetic flux density as a function of z, as a function of this dimension, over the length of the cable. Okay. Now, if we do a little bit of math and magic here, we'll put a 1 over L in front of our integral, and then just put an L in our constant term here. This term here is the net integrated average current. So this tells you that the inductive crosstalk is determined by the net integrated average current, not so much by the peak current. And if we have a constant culprit current over frequency, then again, per Faraday's law, the induced EMF is the time derivative of the coupled flux, which is j omega times the flux density times the area, which is proportional to frequency times the current. Okay. But the victim cable impedance is mostly inductive. Certainly at higher frequencies, we can assume that's basically going to be the loop inductance that's going to dominate the impedance. So that loop impedance is also going to be proportional to frequency, j omega times the inductance. So if you've got potential, a couple potential increasing in frequency, but impedance also increasing with frequency, then that's going to give you a constant victim current over frequency for a given culprit current. So it's kind of another way of looking at how the victim current in the worst case can equal the culprit current. And just going back to the dipole session, just on the Hertzian dipole, to make your eyes glaze over. These are the traditional textbook equations for the electric field from a Hertzian dipole. And if you look in the far field, you have this constant term, just a whole bunch of constants here. So you have a constant term times the current times dl. So here again, just doing this little mathematical manipulation, we see that far field emissions are also determined by the net integrated average current and not so much by the peak current. Few words about so the RE102 limits, the benchmark limit we tend to use is this fixed wing internal limit, so less than 25 meters nose to tail. And I have a whole app note where we've gone through just the analysis and test results showing the transfer function, the electric field as a function of current. That gives you this curve here. Happy to provide that app note for anybody who wants it. It's on the Teams page. But so our radiated emissions limits below 200 megahertz are generally unnecessary on Goddard platforms. We don't have radio receivers. They're way more stringent than is necessary to control crosstalk. So we can use emissions as common mode, conducted emissions and susceptibility limits with much more meaningful and sensible limits and give you an apples to apples comparison. This just shows you that if you go through that correlation to what common mode current should theoretically meet the equivalent radiated emissions limit, it's significantly more stringent than anything we need to control crosstalk below 200 megahertz. I think in the interest of time, I'm going to skip forward on some of this, but I'll repeat my mantra that you ultimately will have to consider every conductor, every cable as a transmission line. So of course, if you got space wire or something like that, the individual cable internally is a transmission line. It must be for those high data rates to have good signal integrity and work. But the cable itself is going to form a cable or effectively a wire above ground transmission line. So this is what I was talking about earlier, that with the default 5 centimeter height above the ground plane for the mill standard, that's going to give you a characteristic impedance of about 300 ohms. You just work through the math, and I show you how to do that in other sessions, in the transmission line session. Okay. And in the typical case, wire above ground transmission line represents a shielded cable with the shield terminated through chassis at both ends. So you're not terminating it in Z0, you're terminating it in a short. That's what you want, right? You want the shield to be terminated to the chassis at both ends. So that will give you a mismatched impedance with reflection and standing waves. I mean, it will, physics says so. You really have no choice in the matter. And so you'll have reflection coefficients at either end, just given by the difference of impedances over the sum. And then you'll get the standing wave ratio at either end. Standing waves from the shorted termination at either end. This is just a little animation. Oh, it looks like Teams is actually cooperating. It doesn't always like these animations. This just illustrates the general principle of a standing wave. You can take the blue trace as your sent wave, and then you're terminating it in a short. Then the red wave is your reflected wave, and it's basically going to be the negative of the send wave at the short, because at least the voltage, this is representing the voltage at a short, the voltage is going to be 0. So your reflected wave has the opposite magnitude of your send wave, and then the black is the combined standing wave. What the net result is. So, some math magic to make your eyes glaze over, but I'll sort of slide over this. But I go through a lot of the math in the backup slides. You can look at that. Any mathicists can look at that if you wish. But when you have a matched line, these reflection coefficients go away, and you have a much simpler expression here. But if in the transmission lines session, I go through this input impedance of a lossless transmission line, and the ultimate takeaway from all that analysis is that when the length of the line is an odd multiple of a quarter wavelength, the apparent input impedance it sees at that distance away, at a multiple of a quarter wavelength away, is going to be inversely proportional to the physical load impedance. So if that load is a short, it will look like an open. And so you're going to get current nulls at those frequencies. And then at multiples of a half wavelength, then the apparent input impedance at that distance away will look like the physical terminating impedance. So a short will look like a short. So the net result is that if you look at the current here for a given drive potential, I'm just using 2 volts and a 1 ohm source impedance and a 1 ohm load. You would expect, and the DC model tells you should get 1 amp, which is what you get at low frequencies. But when you go through the transmission line analysis and sweep that source potential over the frequency, you're going to get this pattern of peaks and nulls as we just described here. So at odd multiples of a quarter wavelength, you're going to see a high impedance, even though you've got a low impedance here. And I'm just saying, I'm using 1 ohm because XL doesn't like 0. It doesn't like dividing by 0. But you're going to get that low impedance is going to look like a high impedance out here. So if it's a high impedance, you're going to get a current null. And then at multiples of a half wavelength, the low impedance will look like a low impedance and you'll get a current peak. It'll basically be the same current that you get at low frequency. So an example here for a 4-meter cable, 2 meters in front of the ground plane and 2 meters to the wall, you're going to get nulls at odd multiples of just under 19 megahertz and peaks at multiples of 37.5 megahertz. So the peaks and valleys will vary along the cable as a function of frequency. So the traditional approach, as it were, or at least the recommendation, is in order to properly capture all the peaks, the receiver and analyzer should be placed in max hold mode, and the current probe should be physically scanned along the length of the cable as you take multiple sweeps. Now, I've almost never seen this done. It's really kind of, it's the way it kind of should be done, but I have never actually seen this done because, you know, it's a little bit of a pain. I don't think it's that much of a pain, but it's just, if you're not physically present to make sure it gets done that way, you know, a lot of times it just doesn't happen that way. But when you work through the math, oh, okay, I'm sorry, I'm getting ahead of myself. But so for low frequencies, when the length of the cable is much less I'm sorry. For when the length of the cable is more than 1/10 of a wavelength, choosing a single probe location adjacent to the EUT, so that's basically where you're going to have this characteristic we're talking about here. When you're at the EUT, so when you are at a distance from the termination point, you could get either a false positive, a test failure due to an exaggerated emission level, or a false negative. The test, especially at these nulls here, the test passes because the way you're making the measurement masks a real emission that could pose a problem. If your EUT is, if I'm showing the current probe here in this figure, but if the default sometimes is people want to put the current probe here at the EUT, and if you do that, you're at a distance from a shield terminated at the access panel or at the capacitor bank, and you're going to get this pattern of peaks and valleys. And if you're at an odd multiple of a quarter wavelength, so in this example, you know, of an odd multiple of 18.75 megahertz, you're going to be in this null here. So your EUT could have tremendous emissions at this point, but because you're seeing a high impedance at that frequency, you will never see it. And that's the worst possible result, in my opinion, a false pass. You're getting a false sense of security that everything is okay when it's not. And then that could bite you at the integrated system level because you didn't do the measurement right. So if you place the probe at the load end, shows you here, if we place it at the load end, like the previous figure shows, it'll bring up the nulls. Right, it'll bring up the nulls to basically what they should be for a matched load. I worked through the math in the backup charts to show that. That still leaves the peaks, which if that's the only option you have, then at least you're getting a worst case. Right, I'd rather have an exaggerated level here, you know, based on the test method that forces me to look at something than a false pass or false negative, as it were, that's masking something, right? Because here, this doesn't give me anything to look at. This makes me think I'm passing. This at least tells me, okay, there's something I should look further at, and maybe I'm getting an exaggerated reading due to how I'm making the measurement. So when you're at lower than 30 megahertz, you use a standard current probe and place it as close to the termination as possible. So at the where the shields are connected to the access panel for any shielded signal cables, and for power leads, put them right near the feed through capacitors. So that's effectively your load end. That's going to capture the maximum or peak current at all frequencies. Now, ideally, we'd want a normalized measurement of emissions that's independent of cable configuration, a matched transmission line. This will provide an assessment of the frequency content of emissions from the UT that may be more effectively used to assess compatibility with the rest of the platform in the flight configuration. So again, remember that when the length of your cable is an odd multiple of a quarter wavelength, your input impedance is going to be inversely proportional to the physical load impedance. So a short will look like an open and vice versa. So if you increase the load impedance, the physical load impedance, it will reduce your apparent input impedance. So it will increase the current at the nulls. And when you're at the half wavelength resonances, increasing the physical load impedance will also increase the apparent input impedance. So it's going to decrease your current at the peaks. So it's basically going to provide some damping. If you go back to the figure here, it'll basically squash both of these resonances. Like when you detune a resonance, that's what you're doing. You're reducing the levels of these peaks and getting them closer to what the nominal level would be going into a matched load. And all right, there's a lot of math here that probably not too many other people besides me are interested in. I'll let you peruse this to your heart's content when I make the slides available. But just the idea is that when you are able to terminate the line in a matched impedance, you basically are detuning those resonances and getting more of a normalized reading of what the EUT will be putting out into a matched load. Okay. And I'll just give you a little sneak preview of this for when you're looking over the charts. Everything I've been talking about before up to this point is really just looking at the total magnitude. It's ignoring the time dependence. When you look at the time dependence and take a snapshot in time, okay, when you're at one of those half wavelength resonances, we'll look here at where the current is basically a maximum at either end of the cable and a zero in the middle. Then you're going to get the flux, the magnetic flux generated through a victim is going to have that same profile. Okay, it's going to be maximum at either end and zero in the middle. Well, the total integrated flux through the loop, when you're at that moment in time, is going to be zero. That's going to be your maximum net field cancellation. Okay. And also your average current in your culprit is going to be zero. And then, but then when you're at a different snapshot in time for that same half wavelength resonance, where the current's zero at either end, but a maximum in the middle, the magnetic flux density is going to have that same profile. So that's going to give you your maximum net coupling. Okay. So the net result here that I'll kind of skip through this is that when you increase the damping resistance, it's going to reduce the peak amplitude in these snapshots in time corresponding to the maximum field cancellation. So you're already at the maximum field cancellation, so it's not really going to have an impact at those levels. When you increase increasing the damping resistance has no effect on the peak amplitude at the snapshots in time corresponding to maximum coupling. So basically, when you put that damping resistance in there, it's not really affecting the average current. Okay, I realize this is a lot of stuff to go through, but bear with me here. We'll get out of theory here in just a moment. But just when you look at these snapshots in time, and look at these. This is a set of graphs of current over the length of the wire. Okay, so here's where you have a half wavelength resonance. The current's a peak in the middle and zero at both ends. This will give you your maximum average current and your maximum coupling, maximum magnetic field coupling. And this is when you are this is when you're at a half wavelength. When you go to a full wavelength, then you're getting complete cancellation. The total integrated current is zero. the total, that total integrated average current over the length of the wire is zero. So there's zero magnetic flux at any of these even multiples of a wavelength. So we can basically ignore this column now. But when you go to a 1.5 cycles, when the cable is equal to 1.5 wavelengths, you will get 3 times, or you'll get cancellation from these first 2 portions of the waveform. And then your net coupling is going to be a function of this last 1/3 of the waveform here. So you will have 1/3 of the maximum coupling. And likewise, when the cable is 2.5 wavelengths or 5/2 of a wavelength long, your coupling will be limited. These 2 cycles will cancel, and you're going to be limited by the contribution of this last 1/5. So now you will be at 1/5 of the total coupling, or 1/5 of the maximum coupling. So where your P0 is the peak amplitude of the coupled flux for n equals 1, right? Then omega naught is the frequency for which n equals 1, or L is half of a wavelength. The net coupled flux decreases with frequency along with the average current. So then your coupled potential into the victim loop, let's see here, that's my apologies here, I was in my train of thought. But the last statement here, the frequency dependence cancels. There we go. The frequency dependence cancels. The coupled potential will have a constant peak amplitude with frequency for a given culprit current. Okay. So enter the absorbing clamp, and a matched termination at all frequencies would reduce the current emissions at frequencies for which the cable is electrically short, so less than 1/10 of a wavelength. So if we were to actually put a physical 300 ohm resistor on this cable, we would actually reduce the emissions at low frequencies. We don't want to do that. Also, inserting such a connection would require breaking the shield termination, right? You want the shield to be terminated to chassis for maximum effectiveness. So if we were to insert a 300 ohm resistor, we'd break the shield termination and insert a 300 ohm resistor. That's neither desirable nor practical. You're going to totally compromise shielding effectiveness, and we don't want to do that. So enter the absorbing clamp. This is a device that has been used for many decades in CISPR 16. It's a current probe followed by a series of ferrite ring absorber elements. It adds a resistive impedance above 30 megahertz and acts to isolate the rest of the cable, minimizing the standing waves associated with signals on an electrically long mismatched transmission line. This was specified for the space shuttle program to address radiator emissions below 200 megahertz. And in fact, in the space shuttle EMC document, the SLE triple ball 2 document I mentioned last week, this is actually part of the RE102 test method. This is the RE102 test method below 200 megahertz. In GEVs, I just separated out to be a conducted emissions measurement. But I found it very interesting when I first came across this approach. It was actually mentioned as an RE102 test measurement technique. Now you have to orient the clamp accordingly, and we're running out of time here, so I'm gonna wrap this up. So just show that below 10 megahertz, the absorbing clamps will actually reduce the measured current. So it's not terribly desirable for low frequency measurement. Another interesting thing is that below 30 megahertz, these peaks and the nulls that you see in the measured current actually shift because you are adding inductance. So you're adding a high mu material in there. Remember, the speed of light is 1 over the square root of mu epsilon. So when you're putting a high mu material in there, you are going to change the speed of propagation through that medium, and so you are going to shift those peaks. But at above 30 megahertz, we see that we do this detuning that I was talking about. The peaks come down and the nulls come up, and you get more of this kind of normalized indication of what emissions the EUT is going to put out into effectively a matched load. It's not perfect, but at least you get less of this variability that's going to be very dependent on your cable layout. And then just one other point to be made here is, let's see here. So the dashed line is no absorbing clamp with a shorted termination. So that's basically the figure we've been looking at. And with the absorbing clamp, with the shorted termination is this dark blue line. And so the red line is an open termination. So with an open termination, you see the pattern of peaks and valleys inverting, right? But then when you put the absorbing clamp in there above 30 megahertz, it's pretty much indistinguishable from the measurement with the absorbing clamp with the shorted termination. So that tells you that the rest of the cable and how it's terminated don't play a significant part anymore. You get more of a normalized reading of what the EUT is emitting, and it's less dependent on the specific lay of the cable. And now here we'll pick up next week with measurements in the lab. But I'll jump to my summary charts here. So RE102 below 200 megahertz is not generally needed or useful on Goddard programs. There are no antenna connected receivers. If you do have an antenna connected receiver, then yes, you should certainly do RE102. Common mode conducting emissions measurements on cables will provide a much more direct and efficient tool for assessing the risk of crosstalk, which is our dominant concern at these lower frequencies. So for a typical case of a shielded cable, with the shield terminated to chassis at both ends, the cables must be considered as wire above ground transmission lines with shorter termination at each end. This will give you a current distribution with a predictable pattern of peaks and nulls. And the nulls will be at odd multiples of lambda over 4, quarter wavelength, and peaks will be at multiples of a half wavelength. So that's, realize the math gets intense and causes a lot of people's brains to melt. But if you can just take that image with you, that if you're using a standard current probe to make these types of measurements, that you will get something that looks like this, and to varying degrees, right? But if you start seeing things that look like nulls and peaks, just understand your transmission line physics, and you'll have a better understanding of what you're looking at. You know, because this is governed by physics, right? Just transmission line theory tells you that this is what's going to happen. So for a low impedance termination, which is your shielded cable with your shield terminated to chassis, or your power leads terminated to the capacitor network, that maximum current will occur at the termination, so at the far end from the EUT. So when using a standard current probe, place it at the load end, so either at the capacitor network for your power leads or at the feed-through plate for your shielded signal cables. The absorbing clamp is an alternative option for higher frequencies, so generally above 30 megahertz. It measures the approximate average current, gets closer to the ideal normalized measurement of the EUT emissions that are largely independent of the cable configuration. And the absorbing clamp can be a controversial option, and so I just mention it as an available option should you choose to use it. I think generally speaking, we use the standard current probe approach. Just know that you will get an exaggerated high reading of currents at those peak resonances. But if you're still compliant with the limit, which we are in most cases, then you're okay. You know that you're getting a worst case. But if you are seeing some strange things at those higher frequencies, you might want to get the absorbing clamp out and make some additional measurements with it, just to give yourself a more full data set. So these common mode conducting emissions measurements can and should be performed as an early diagnostic in the hardware development lab well in advance of official EMI testing in an anechoic chamber. They're quick and easy to perform with clamp-on probes, and they provide you invaluable information to help identify and diagnose potential problems. Quarry details are provided in GES. And 1 minute past 11 o'clock, I can hang around for a few minutes if anybody has questions. Anybody still out there?
Yep.
Any questions?
So John, if you terminate in the characteristic impedance of your transmission line, in general speaking, that characteristic impedance would be a resistor on that far end. So you would dissipate power, and in most application, as a mitigation strategy, you may not be able to do that, but I realize that when you're talking about how to test and see the results of any EMI outage. But in terms of a solution, would you say, hey, try to terminate maybe an AC termination of that to damp those ringing caused by the transmission
For
line?
a composite cable bundle with the shield terminated the chassis, I'm not talking about messing with that connection at all. That was just a discussion point that
Okay.
just in theoretical terms, if you treat a cable above ground as a transmission line, that putting a 300 ohm resistor out there would at least theoretically give you a normalized, if you're terminating it in its characteristic impedance, it would give you a normalized measurement of the actual levels coming out of the EUT without the cable configuration of changing that based on the resonances, based on the standing wave pattern on the cable. That was just a purely theoretical construct. I am not in any way recommending that you put a 300 ohm resistor out there where you have a shield that's terminated the chassis. So,
Okay.
so the point of the absorbing clamp is that it kind of effectively gives you that without having to mess with your cabling. So, I mean, if you've got a shield that's terminated the chassis, that's exactly what it should be. So I'm definitely not saying to do that. I mean, I said that in the chart that there's no reason to do that. It's just that just introduces the general concept of, how do you deal with some of these peaks and valleys? I think the larger point I didn't really make is it's always ideal to come to an EMI test with fully representative flight cables. I mean, it's ideally if you bring the actual flight cables. That almost never happens. People don't generally want to, bring flight cables to an EMI test. They'll make test cables, but they need to be flight representative. And if they're the flight lengths, so much the better, but that's not always feasible either. Sometimes you're building test cables before you know your flight length, so you've got to, make your best guess as to what those are. So the important thing is for flight representative is in the cross section. Like your twisting, internal shielding, and shield terminations must be flight representative to be a meaningful test. But when it comes to the lengths, if those lengths are different from what they will be in the flight configuration, which they very likely will be, then that pattern of peaks and nulls is going to change. It's not what you measure in the EMI lab it's not those pattern of peaks and nulls is going to look different from what you may have on the spacecraft. So it's just important to keep that in mind when you start seeing those kind of resonant behaviors at those high frequencies. That's a function of the cable configuration and specifically the lengths. That's going to govern that pattern of peaks and nulls over frequency. And if that's different from the flight length, that pattern of peaks and nulls is going to be different. And it can be a little tricky to correlate what you're seeing in the lab versus what you're likely to see in the flight configuration. So that's just the word of caution about doing these measurements. When you get up into those higher frequencies, you have to be very careful about interpreting the results. I hope that helps.
Okay.
Anybody else have any questions?
Got a ton of them, but probably better let me get my information together and ask you later. I
That's
got the
fine.
EMI chamber over here at Wallops. We're setting up and got a ton of questions for you later on.
Okay. Yeah, feel free to shoot me an email.
Thanks.
I love your icon, by the way.
Likewise.
It's oh, just he's one of my favorite cartoon characters. You have made me very angry. Just quoting Marvin there. That's or Marvin, of course, Marvin.
I'm feeling much better now.
I was just quoting Marvin, not actually expressing that as a genuine sentiment at the moment. So.
I've had my required anger management class.
Well, just seeing Marvin there just helps me with mine. So thank you.
Thanks.
All right. Anybody else? All right. Well, thank you all for joining up. I'll do this same session again tomorrow, and then we'll start looking at lab work next week. Have a good day.
Thank you.